Hello, and a very warm welcome to our webinar event today, brought to you courtesy of the SPE P&A Technical Section and the American Association of Petroleum Geologists. My name is Alex Lucas, the Asia Pacific representative of the SPE P&A Technical Section, and I'm currently based here in the wonderful city of Kuala Lumpur in Malaysia. I'm very pleased to be joined here today by my distinguished co-host, Susan Nash of AAPG. Susan, if you wouldn't mind.
Thank you very much. It's a pleasure to be here. I'm Director of Innovation, Emerging Science and Technology, and it's just really a pleasure to do so many things with SPE. I just got back from OTC. We have where we are a partner in the Offshore Technology Conference, and then in June, SPE and AAPG and SEG are partners in the Unconventional Resources Technology Conference that will be from June 9th through 11th in Houston. So thank you. We have a wonderful guest and really appreciate everything that SPE is doing here to make this happen.
Thanks very much, Susan. So Susan and I will be your hosts and moderators today. The event will last approximately 60 minutes, but it won't have a hard stop. We encourage you to ask questions throughout, which we will use to fuel our discussions. But please also feel free to use the chat function to ask questions. Many of you will be joining via LinkedIn, but if you're experiencing technical difficulties, you can also try the alternative option via the YouTube link provided on our LinkedIn page. This event will be recorded and will be available on demand via our various platforms. So before we get started, it's of course my duty as an SPE representative to give a quick plug for the Society and encourage any of you out there that are not currently members to please consider joining the SPE so that you can access the many benefits of being a member and also participate in our technical sections for P&A and well integrity, both available through SPE Connect and LinkedIn. So before we get started, a couple of quick updates from myself. For those of you in the European region, I would just like to highlight that the SPE Well Decommissioning Conference 2025 will be taking place next month, 10th to the 11th of June in Aberdeen in the UK. This really is a first-class event for well P&A practitioners, so I'd really like to encourage those of you in Europe to attend if you can. And Susan, I think you've introduced the event, AAPG event, just a moment ago. Anything further from your side?
No, I just want to thank you, Alex, for facilitating and being such a wonderful host.
Thank you very much for the flattery. Okay, so with the formalities out of the way, it's time to get down to the main event of our webinar today on why shales make much better annular well barriers. So everybody, it gives me a great pleasure to introduce the presenter of our webinar today, Dr. Erik van Oort. Dr. van Oort is, in my view, one of the most accomplished engineers and scientists of our discipline and is a towering giant of petroleum engineering. And I say towering, not just because he's quite a tall Dutchman, but also because he's someone who's made a huge contribution to the body of knowledge of both our industry and our society as an SPE distinguished lecturer over the past 3.5 decades, with over 150 SPE publications to his name. Erik is Professor in Petroleum Engineering at the University of Texas at Austin and is currently the holder of the Richard B. Curran Centennial Chair of Engineering and is a recent winner of the Lockheed Martin Award for Excellence in Engineering Teaching. He is a world-class expert in drilling and production and leads the Rapid Industry Affiliate Program at UT Austin's Cockrell School of Engineering, a program proudly supported by a host of well-known operators and service companies across the industry over the last decade. His areas of research and professional expertise span a vast range of areas, including well construction, drilling automation, real-time monitoring, wellbore geomechanics, drilling fluid design, well integrity and zonal isolation, well plugging and abandonment, geothermal drilling, and CCS. He also holds a number of US and international patents on drilling techniques and associated best practices, drilling fluids, and wellbore stability, among others, and has recently published his 1,100-page opus, Managed Pressure Drilling Fundamentals, Methods and Applications, which I have no doubt will become the definitive manual on the subject. Prior to joining the University of Texas, Dr. Van Oort led a very successful career at Shale, where he held a number of positions such as technical expertise holder and deep water drilling advisor, and most recently served as the onshore gas technology manager. Eric's talk today, however, will focus on the subject of shales as annular barriers, a subject he has been researching intensely since 2018 and has resulted in a series of groundbreaking research papers. The work has shown how the remarkable properties of shales can be simulated to form tenacious and resilient annular seals, and how they respond to pressure, temperature, and chemical changes, and all in all, why they make much better than annular well barriers. So, ladies and gentlemen, you're in for a real treat today, as you're in the hands of a masterful scientist and educator. Eric is someone who makes you feel more intelligent just by listening to him. So sit back and enjoy learning while shales make much better annular well barriers. So without further ado, Eric, over to you.
Thank you for that lovely introduction, Alex. And I feel that with that build-up, I can only disappoint our audience now. There is the expectation is sky high.
No pressure. No pressure. Relax.
We're counting on you.
But let me tell you something about the indeed remarkable properties of shales and why they make potentially much better barriers. So as Alex already indicated, I'm a professor at UT Austin. I've worked for many years for Shell Oil Company, and I'm now right now, of course, a professor at UT, teaching drilling and completions related courses and running a research consortium called RAPID. And what I'll do in the agenda is I'll introduce RAPID a little bit to you. I'll give you an introduction to shale as a barrier, or what is indicated by the acronym SAB. I'll talk about how we do shale as a barrier experimentation and what the effect is of artificial heating, which turns out to be kind of an accelerating effect on shales. We'll talk about shale barriers for carbon storage wells and why I think they're uniquely suited for carbon storage in particular. We'll talk a little bit about the healing of poor quality cement by shale. And then I have some conclusions. Personally, I really like this acronym SAB. I'm a child of the 60s, 70s, and 80s. And in the Netherlands, where I grew up, about the coolest car that you could have was a Saab 900. No longer being made, unfortunately. Fantastic car. You see a picture of it right there. So the acronym always makes me feel good about my past. As I said, I'm the director of RAPID, which is, if you want, an industry consortium. We call it an industry affiliate program. And I run that together with 4 other professors. And RAPID has 5 pillars, 5 kind of categories that it's involved in. It works on sensors and measurement systems for drilling primarily. We work on advanced modeling, controls, and digital twinning. We've recently, for instance, developed the counterpart to manage pressure drilling and temperature, which we call managed temperature drilling, where you automatically control the temperature in a well, which will be important for high pressure, high temperature wells and geothermal wells. We work on data analytics using AI and machine learning. Our customers give us large data sets that we analyze using AI and machine learning. And then a separate group that works on robotics, or what some people call mechatronics. And what I'll talk to you about today falls within the category of sustainability. So on the sustainability side, we work on geothermal, carbon sequestration, and hydrogen wells. We look very much at alternative cementing and zonal isolation, and shale as a barrier kind of falls under that. And then overall kind of looking at well integrity, well P&A, and potential well reuse and repurposing, for instance, repurposing old oil and gas wells as geothermal wells. So it's a very specific kind of research direction for us, but what I'm showing you today, RAPID is about much more than just shale as a barrier. We are fortunate enough to have very good industry support from companies large and small, from operators and contractors. This is the preliminary tally of the 2025 RAPID sponsors, and you're going to see the companies. And without them, we simply wouldn't be able to do this research that I'm going to be presenting to you. So we're very grateful for that. And I hope you will see, is we work on very applied things. We do applied research that can be implemented by our members and sponsors out in the field. It's not just research for research's sake. The idea behind shale as a barrier really came from the North Sea, where people were looking at opportunities for rigless abandonments. Abandoning wells offshore is very expensive, and there was a feeling that we should minimize those costs while still doing very competent well abandonments. And if you have the situation that you see here on the left, where you have an annulus with maybe a low top of cement, and there is some CO2 leaking on the backside, you have gas migration to surface, maybe sustained casing pressure and annular vent flows. What the regulator would require of you is that you section mill casing, or you cut and pull casing if you can do it, and then set an open hole cement plug to isolate this. And that is, of course, a task that requires a rig and is an expensive proposition. Wouldn't it be nice if there is a shale formation behind the casing that can kind of come into the annular space and form a barrier? And if you can then qualify that barrier, either through testing it with pressure tests, or maybe qualifying it strictly through cased hole logging methods, then you can just set an abandonment plug in the well itself, and that you could potentially do rigless. So that was the original idea behind shale as a barrier. As I will show you, this idea has kind of evolved from kind of remediation of old wells and providing kind of plugging and abandonment opportunities, to maybe even considering these shale barriers as integral part of well designs. But I'll come back to that later in the presentation. It's been well documented in papers by companies such as Aker BP, Equinor, Total Energies, that this is a real phenomenon on cased hole bond logs. It can be seen that for shale sections above the top of cement, there is good bonding. So on cement bond logs and VDL logs, you see clearly that shale has bonded to cement. And then when these bonded sections were tested with pressure tests, they were shown to provide barrier integrity. The image on the right is from a paper by Aker BP, where they actually observed over a period of several weeks the formation of a barrier behind pipe. So you can see the progressive development of good bonding behind the casing. So this is a well-known phenomenon that people have started to actively exploit. We do the shale as a barrier tests in a lab in Houston called Metarock Laboratories. They have wonderful infrastructure. If you're ever in Houston, I would certainly recommend that you make a visit and see Metarock. It's amazing. The tests that I'm going to show you are some of the most advanced rock mechanics tests ever attempted. And Metarock has the expertise and the ability to kind of build and operate customized rock mechanics equipment, which we need for our SAP tests. So we actually have 3 different types of setups. the test setup where we do our base tests and do our various heating experiments, which I'll talk about. We have a test specifically dedicated to cooling of the wellbore and testing the effects of shale barriers for carbon storage wells. And then we have a large-scale new setup where we do what we call new SAAP tests that are dedicated to looking at the effect of shale on compromised cement sheets. And I will be talking about these three types of tests in the following. This is a typical test setup. So what we do is we take cylindrical shale samples. We place them in a core holder. We'll have a top platen and an end platen, which actually have fluid reservoirs in them. And those fluid reservoirs, the upstream and the downstream reservoir, are actually connected to each other through the annular space that surrounds a casing that we have on the inside. And that casing, in many of our experiments, is just a steel insert. But as you will see with the carbon storage test that we do, we can actually make that a hollow casing string as well, in which we can circulate cool fluid. We can place the sample with the end platens under confinement. So we have radial and axial confinement. We apply triaxial stress. We can apply pull pressure and an annular pressure if we want. We can heat the sample to pretty much any temperature that we would like. And typical for our base tests, we bring the sample back to kind of in situ stress, temperature, and pressure conditions. Here you see the mounted sample. So you see the casing insert in the middle, and then we have an open annular space, and then you see the shale sample around it. And that sample is jacketed with a sleeve for which we can then apply radial stress. And you see we have a cantilever strain bridge around the sample. We have axial LVDT, so we can measure axial and radial strain when we are conducting a SAAP test. We know that the mechanism of annular closure is creep. So this viscoplastic deformation of the rock. I always explain this to people who are not rock mechanics experts as creep is basically a rock that thinks it's a fluid. So it has some identity issues associated with it. And you can see from our measurements, from our strain measurements, that we indeed see creep. In the inset here, you see kind of the textbook creep behavior with primary and secondary creep. Basically strain deformation as a function of time under the influence of downhole pressure and temperature. And in our tests, we indeed see kind of textbook creep behavior. We see primary creep and then the secondary creep that ultimately closes in the annuli. And so the animations from ANSYS fluid kind of indicate that. One thing that is kind of unique to the setups that we use is we have this upstream and downstream reservoir, which initially are connected through an open annulus. And during the test, what we do is we probe the annulus. We probe basically its state, if it's open or closed. And you see these kind of pressure transients here. In figure A, we're pulsing the top pressure and recording what is going on with the bottom pressure. And of course, when the annulus is open, the two pressure profiles follow each other very directly, right? There is just open communication across the annulus. But when the annulus closes, and we get, of course, positive confirmation that the annulus closed, if you then pulse up the top pressure, you see a delayed response on the downstream side. And that indicates that what we now see is no direct communication between upstream and downstream. We see pressure diffusion through a newly formed shale barrier. And the time scale for this pressure diffusion lengthens over time. And from these transients, from this transient behavior, we can actually determine the permeability of the shale barrier. So while the test is going on, we can see how the permeability of the shale barrier develops. Initially, when the barrier forms, the barrier is already as good as a cement barrier. So it will have a permeability of maybe a few microdarcies. But then, as you can see, as we go from B to C to D, and I hope you see the lengthening time scale, the shale permeability becomes lower and lower. And we've never done a test for months on end. That would be very expensive to do. But we think that ultimately the barrier will become the barrier of with a permeability of the native shale, so in the nanodarcy range. And when it, of course, achieves nanodarcy permeability, the barrier is about 1,000 times as good as a shale barrier permeability-wise. And this is one of the reasons why I think shale make better barriers. This is absolutely crucial to verify the barrier, to verify its integrity, and you'll see a lot more of these plots in the remainder of the presentation. What we also do at the end of a SAP test is we do a breakthrough test, pretty much a leak-off test. One thing that we do is we ramp up, in the previous experiments, we pulsed up the upstream pressure. Now we ramp it up, and we ramp it up all the way to see breakthrough on the other end. So we can ramp up either the bottom pressure and see the breakthrough on the top, or ramp up the top and see the breakthrough on the bottom. And that gives us an indication of how strong the barrier is and how much differential pressure it can take. And as you can see, this is an actual measurement. You see that when these barriers form, they are very, very good indeed. In this case, the differential pressure is 1,000 psi over a sample that is only 3 inches. So a 3-inch shale barrier, in this case, can handle 1,000 psi of differential pressure. In fact, the theoretical maximum is the value of the minimum effective horizontal stress, which in this case was, in this experiment, was about 1,250 psi. So we're getting very close to that 1,250 psi in this particular measurement. So just think about that, right? 3 inches of shale holding competently, without leakage, a differential pressure well over 1,000 psi. And then after the testing, what we do is we observe the sample. Here you can see that indeed a barrier has formed, that annulus is fully closed. And then we can analyze the sample before testing and after testing on CT scans. So that is basically the explanation of the experiments that we do. But I'll show you different variations of this type of test that we have performed. And there's some amazing results associated with that. So you may wonder which shales form barriers naturally, which ones do this out in the field, which ones were the ones that were diagnosed by these North Sea operators as having formed barriers spontaneously. Well, we typically know that it's shales that have a high total clay content with significant free and mixed layer smectite, with a high porosity, high cation exchange capacity, relatively low matrix cementation, so low quartz and carbonates content, low strength, low stiffness, low friction angle, and low compressional wave velocities. They're typically kind of shallow, relatively young shales from a geological standpoint, that also have a tendency to cause shale-related boreal instability problems during drilling and tripping. So if you have a shale in a relatively shallow intermediate hole section, that typically gives you problems during drilling, then you're pretty much in business when it comes to forming annular barriers, annular shale barriers spontaneously. But what if a shale doesn't form a barrier spontaneously, or only forms it very slowly? Well, we've figured out over the years that there are kind of 3 methods by which we can stimulate these barriers artificially. And the 3 main methods are thermal stimulation, pressure shock, and chemical annular fluid change. Thermal stimulation is basically achieved by letting a heater down the well And from the inside of the casing, kind of heat the casing and also the formation behind casing, and then increase the near wellbore formation temperature, which greatly accelerates any creep tendencies. It can be increased by orders of magnitude, as I will show you in a moment. And this is actually practically feasible. There are right now companies that provide such heaters by which this could be accomplished. And the nice thing about this method, and this is the reason why I'll predominantly talk about this in the following, is that it doesn't require annular access. So you don't have to go and perforate casing strings in order to get access to the annulus. With heat, through heat conduction, you can do it from the casing string itself without having to compromise it. If you want to use pressure shock, pressure drop, or chemical annular fluid change, you will need access to the annulus. So you need to perforate and expose the annular the annular space to either a pressure drop or a change of fluid. So I'll talk mainly in the following about heating. This is the first shale as a barrier test that we've ever done, which was done on the Lark Shale from the North Sea. It's again one of these highly reactive shales with a high clay content at a relatively shallow position in intermediate hole, typically 12¼ inch hole that's being drilled at an in situ temperature of about 55 degrees C. And when we did the test on this particular shale, we found that we saw closure of the annulus in about 18 days running this test. So the green line is the creep behavior. You see the pulses there in red and orange. You see that those pulses kind of overlap each other until we get to about 18, 19 days where you see a separation between the pulses. So we pulse the upstream, which is the red, and we monitor the downstream. And now you see kind of a clear separation, which indicates that the annulus has closed. So 18 days in the lab environment. And from this experiment, we could actually extract creep parameters that we could then apply to a very nice finite element model that we have for the actual field situation. So we can derive the parameters to model, for instance, the annular closure of 9 5/8 inch casing in 12¼ inch hole. And we found that this typically then takes about 3 months in the field for an annulus to close, which is in very good agreement what has actually been observed out in the field. But let me now show you the amazing effect of heating. We have the ability to do these tests at different temperatures. We can go all the way up to 250 degrees centigrade, so about 500 degrees Fahrenheit. And as I already said, the creep phenomenon is strongly influenced by temperature, and that influence is non-linear. So here you see the Lark Shale at 55 degrees C. Again, this kind of textbook creep behavior. If you wanted in a rock mechanics book to show creep, and this is your curve, right? This is the figure that you would use. But look at how much faster, how much more violent it is in a sense if you go to 150 degrees centigrade. At 55 degrees centigrade, as I said, we saw closure of the annulus in 18 days. At 150 degrees centigrade, we see it in less than a day. So at that point, we see this full annular closure, full annual barrier formed within less than a day. We've studied this phenomenon quite in depth. We saw some strange things at intermediate temperatures. It looked like at intermediate temperatures, the shale was radially cracking. And this is because of thermal dilation, pore pressure elevation, so we can explain that. But that kind of cracking goes away at higher temperatures. So if you go to 150 degrees centigrade or beyond, then actually the shale reheals. You see all the cracking, in fact, disappear, and you get a tremendously good barrier. We've taken this all the way up to going to 250 degrees centigrade, and then heating at very high rates. And in this experiment, we are heating at 42 degrees centigrade per minute, so very high heating rate, and it didn't negatively affect our barrier formation. There is, however, and here you can see those barriers formed, right? You can see, and in this case, what we're doing is we're pulsing the bottom pressure and then looking at the upstream pressure, and pulsing the upstream pressure and then looking at the downstream pressure. And you see this, we have a barrier formed in less than 1 day, right? When we start doing the test, our first pulse test, we already have a barrier at these temperatures. And we have an amazingly good barrier formed. In fact, in this particular test, we couldn't achieve breakthrough within the limitations of our experimentation. So we went all the way up to the highest differential pressure that we could get, and we couldn't break the seal between the shale and the casing. So you see actually that there is no breakthrough on the downstream side. In fact, we're pulsing up the bottom pressure here and looking at the top pressure. We don't see any breakthrough happening at the maximum pressure that we could put on the sample. So again, with this accelerated creep rate, we get a very good barrier formed. There is, we believe, a maximum temperature that you don't want to go beyond, and that temperature is probably around 300 degrees centigrade, with optimum temperatures below that, possibly below 200 degrees centigrade. And the reason for that, you see here in some work by Suo et al. In 2020, at elevated temperatures, you see here elevated temperatures, you see basically the mineralogy of the shale in terms of percentage at different temperatures. What starts happening is that you artificially induce diagenesis, so you're transforming smectite into illite. And of course, smectite is your creeping mineral, right? So you're reducing the amount of smectite, and that from a creeping and barrier formation standpoint is not necessarily a good thing. So there is an upper end to this temperature. Don't go treat the shale with heating methods that reach thousands of degrees centigrade, because then you might actually do some harm. You might actually form an illitic shale that cracks and that has a compromised barrier. I wanted to show you these results on the carbon storage test that we've done. And those tests were basically brought to us by Equinor, who are looking at alternative barrier solutions for their carbon storage wells. And if you know something about carbon storage, you know that CO2, liquid CO2, is pretty cold. It's typically handled at -20 degrees centigrade. And then when you inject it into reservoirs, you get additional cooling from what is known as the Joule-Thomson effect. So you could go even beyond that -20 degrees centigrade. Will cool down the wellbore and the adjacent cement sheet. And a big problem is that the thermal expansion coefficient for steel and cement is different. So the steel and cement expand and contract differently. And it will not only contract, it will also expand, because CO2 injection is intermittent. So we will stop in CO2 injection occasionally, and then of course the wellbore will heat up back to in situ conditions. So you'll have frequent cooling and reheating cycles. And this is not good, particularly not for the relatively weak barrier, the weak interface between the cement and the casing. That is a particular weak link. For those of you that are familiar with kind of cement bonding to casing, cement bond strength is probably only about 100 to 200 psi. So that bond is easily sheared. And if you shear it, you will generate a microannulus between the cement and the casing. Now that microannulus could become a leak path for CO2, that CO2 can react with Portland cement. It can react with both Portlandite, which is calcium hydroxide, as well as with CSH gel to form calcium carbonate. Now that CO2 transport can become self-limiting. That calcium carbonate can start plugging the microannulus and any fractures in the cement. But that is a process that is kind of dependent on the dimensions of the microannulus and the fractures. For certain dimensions, the CO2 could just also consume all the cement, and there are CO2 storage wells where indeed no cement has been found in the annulus after a while. So this is a concern, particularly using Portland cement barriers in CO2 wells, CO2 injection wells. So we created with Metarock a separate setup, quite sophisticated one, where the casing insert is no longer a solid cylinder, but it's a hollow casing. And we can circulate either supercritical CO2 in here or, from a practical standpoint, some coolant, and cool down the wellbore and see the effect of cooling on the barrier. So let me show you the results of this, and they're pretty amazing. This is the actual setup. So here you see the pumps that we use for confining and injection. Here's the pressure vessel kind of taken out of the actual triaxial vessel. Here's our chiller. We're circulating coolant. And here's our sample. So in this test, what we did is we took the large shale and we generated a barrier. We did it with heating. So at 150 degrees centigrade, initially, we have a good barrier. And then we cooled it back down to in situ conditions first, which is 55 degrees centigrade. And then we started cooling the wellbore. So circulating the wellbore, and we didn't go all the way to minus 20 degrees centigrade, but we went to about minus 14 degrees centigrade. But as you can imagine, a significant temperature shock. We measure the temperature, but we measure the temperature actually on the outside of the shale sample. So you don't see that all the way going to minus 20 degrees centigrade or minus 14 degrees centigrade in the new wellbore. While we're doing this, we're probing the barrier. And you can already see that if we do these barrier pressure pulse tests, we clearly continue to see the separation between the upstream and the downstream pressure. When we pulse up the downstream reservoir, we see delayed response on the upstream side and vice versa. So the cooling of the wellbore doesn't seem to in any way compromise the barrier. We also did kind of breakthrough tests. We did a breakthrough test without cooling and then with cooling. So before and after cooling, and the result is identical. The breakthrough, maximum upstream breakthrough pressure that we get in both cases was within the experimental error. So again, indicating that cooling appears to have no significant effect on the shale barrier. Then we said, okay, well, this is just one cycle that we've done. Let's do lots of cycles. So let's heat the sample back up to in situ conditions and then cool it back down. And let's do that several dozen times and see what we get. And you can already see what the result was. While we're heating up, of course, we continue to have a good barrier, but when we're cooling down, we maintain the barrier. And in fact, after literally dozens of cooling cycles, we were not able to compromise the barrier in any way. We did this also for a Cretaceous shale, the Shetland shale, provided by Equinor. The Shetland is even better in barrier formation than the Lark. It forms a barrier actually more quickly than the Lark shale. And we saw the same thing. When we cooled the wellbore down, we always saw separation of the upstream and downstream pressure. The upstream reservoir pressure here is inverted because in this case we didn't shield it properly from the cooling. but you can clearly see that there is pressure isolation between the upstream and the downstream side. And again, we went through multiple cooling cycles on this. We did breakthrough tests before and after cooling. So again, the same maximum upstream pressure, no discernible negative effect of cooling on the barrier integrity. And again, here are the cycles for the Shetland Shale. Heating back up, cooling back down. I'm just showing you one cycle. We did this, as I said, dozens of times. Never did we see the barrier being compromised. The last set of tests that I want to show you have to do with the question, can creeping shale heal a compromised cement barrier? So is it possible for a shale to regenerate a barrier in rubbleized cement or in cement that has a microannulus? And for that, Metal Rock built a large vessel where we're taking larger samples. In fact, in this case, we take whole core with a length of about 8 inches and a diameter of about 4 inches, and do larger scale tests. Here you see the test cell. Again, we have an upstream and a downstream reservoir. We have a larger hollow casing string, and in that casing string, we actually have a transducer array that allows us to measure bond logs. So we actually are able to measure cement bonding or lack thereof while we're doing these tests. Here's the schematic of the test. So here's the hollow casing with the transducer array. And then we have a cement sheet, which may or may not be compromised when we start out with the test. And then surrounding it is the 4-inch diameter shale sample. And we have the ability to kind of circulate and change pressure inside the casing. So we have the ability to cycle casing pressure and trying to, for instance, induce a microannulus between the shale and or between the casing and the cement. The first test that we ran was a test with rubbleized cement. So in the annular space between the casing and the shale, we basically put cement fragments. So we basically made some cement, we busted it up, and we filled the annular space with these fragments. And evidently, when you do that, you don't have barrier integrity, right? You can show that in a pressure pulse experiment that you have direct communication between the upstream and the downstream reservoir. However, and I still regret kind of cutting this test short, we ran it for several weeks and we never saw an annular barrier form. When we deconstructed the sample, and you can see that here you see the cement fragments. We did see significant invasion of the shale within these cement fragments. So between the cracks of the cement fragments, we clearly saw that the shale had invaded. And I always had the question that if we would have run the test for a longer period of time, would a barrier have formed? In fact, we are doing that test, we are repeating it right now for a longer period of time and with elevation of the temperature to accelerate the creep more than what we did in this test. So it is possible that with a broken up cement sheet, the shale could invade into the cement and reestablish the compromised barrier. And that's pretty exciting. The other test that we are doing is a test where we have good cement, well-bonded cement, behind the casing. But then what we do is we do pressure cycles inside the casing, trying to debond the cement from the casing. So cycling pressure up and down, and then at some point seeing if we can see breakthrough. And here you can see this result. Here is the barrier that we have before testing. So we have a good annular barrier, good cement barrier, with the typical kind of permeability that we expect for a cement barrier, which is always kind of typically in the range of 1 to 10 microdarcy. And then we go through these pressure cycles and we measure it again. And you can clearly see that there is some difference that has happened before and after, but we still have a good barrier. In fact, we've done these pressure cycles and very severe pressure cycles. I mean, these are 1,000 PSI casing pressure cycles, right? We've done many hundreds of them. And we do see changes in the annular barrier, but we never see the clear formation of a microannulus. And that has given us pause. You could interpret this as saying, well, apparently cement is a much better barrier material than you thought it was, right? Clearly, I mean, we have no microannulus forming. But do understand that outside of this cement, we have a shale with significant creeping potential. So an hypothesis that we have is this. The pressure cycling does create a microannulus. We don't do a continuous pressure test, so we only do it occasionally, and we do it after the cycles typically. So we think that pressure cycling does create a microannulus, but the shale creep acting on the cement sheet kind of closes it quickly, and then barrier integrity is immediately restored. And again, if that happens, or can be made to happen artificially by heating, that would be an extremely important thing. How we're going to be investigating that, and that is again testing that we've lined up for the next months, is conducting these NSAB tests with a cement barrier in a non-creeping material. Could be aluminum, could be a granite, pyrophilitic material or something like that, and see if we can indeed effectively debond and not, of course, have, in this case, a creeping material under the pressure and temperature conditions that we typically do these tests. So it's going to be an exciting time kind of going forward, figuring this out. But this brings me to my conclusions and recommendations. And I hope that I've shown you that only certain shales under certain in situ conditions will creep to form barriers. And this is dependent on various geological factors. Mineralogy is very important. In situ stress and pressure conditions, rock mechanics parameters, right? Strength or lack thereof is extremely important. And then I hope to have shown you that shales can be artificially stimulated to significantly accelerate the barrier formation process. And then thermal heating is probably the most viable way to go for field application, and commercial heating solutions are available. We are speculating that shales that do not creep by themselves could potentially be stimulated to creep with heating, but we've never actually observed this because we've never had those kind of materials where we could verify that. The shale barrier permeability, once formed, is immediately equivalent to that of a cement barrier, but then it drops over time. And we think that if you extrapolate it over long time horizons, you basically get the shale permeability back. And then you basically have a barrier that is caprock, that is intact caprock. You basically have restored the caprock in that case. And as we know, caprock is a barrier that lasts for eons, right? We're not talking years or even hundreds of years, we're talking millions of years. And if we could provide well integrity for that period of time, right, that would be fantastic. We always have the concern about how does a cement barrier behave when we extrapolate to 100, 1,000 years and so on. The barriers, once they form, appear to be very resilient against temperature and pressure cycling, as I've shown you. And it therefore appears very well suited for well integrity in carbon storage wells. And basically should be considered as integral part of CO2 storage well design. And here you go away from using shale as a barrier as part of kind of a remedial treatment during a well P&A exercise to building the barrier in as a fundamental barrier during well planning. Shale is of course impervious to any CO2 chemical attack. And even if it would temporarily be compromised through CO2 cooling, we speculate that when the well heats up back to in situ conditions, creep would again close any void spaces, and you would retain or regain the barrier. Induced shale creep may heal compromised annular cement barriers. I'm using the very tentative term may. We have good indications that this may be happening. And of course, that is something that we will investigate in the near future. And shale barriers, I think, should be considered as structural part of future well designs. I already talked about carbon storage wells, but you might think about this in any type of well going forward, especially if you want a barrier to provide integrity for an indefinite time period until either plate tectonics consumes the wells or the sun goes nova and consumes the earth, right? We don't want these wells at any point in time to start leaking. So what are our knowledge gaps and what will I be working on in the future? We want to know the mineralogical boundaries and in situ condition boundaries for shales, either to creep to form barriers or if they can still be artificially stimulated to do so. Something that particularly the companies in the North Sea are right now very interested in and working this with the regulator is what is the minimum required barrier length of a shale barrier, particularly in comparison with cement. And I feel very confident of saying that shale barriers are at least a factor of 10 better than cement barriers. So if your minimum barrier length is 300 feet, then 30 feet of a cement barrier should be more than sufficient, but it could even be less than that, right? And as I've shown you, 1,000 psi differential pressure can be maintained across only 3 inches of shale, right? Not that I would advocate for a 3-inch barrier, but you see that you could significantly go down on the requirements for barrier length when you have a shale barrier. Then we still would like to find out what is the optimum stimulation method or combination of stimulation methods. What are really the thermal and pressure conditions, if any, where formed shale barriers start to leak? Will they naturally recover in that case? Can they really be used to fix leaking and compromised cement barriers? And that would have major implications, right? Particularly for future well abandonments with wells that have, for instance, currently sustained casing pressure. That would be something that would be very interesting. For instance, in the Gulf of Mexico, if you go to Nelson and Guillot's book on cementing, the first graph that they have in that book shows you the number of wells in the Gulf of Mexico on the shelf that have sustained casing pressure. And it's on the order of about 70% of the total, right? So that's going to be a huge exercise remediating all these wells. Can salts be used for shale as a barrier, right? Can different types of creeping salts be used? I have already been approached by people that wanted to use the Zechstein formation in the North Sea area for this purpose, but I think it's completely unsuitable for that purpose because Zechstein contains these bischofite and carnallite formations that creep at a very high rate. And in that case, you'll have to start worrying about point loading of casing and collapse of casing, which happens, in fact, in the Zechstein if you don't use high-strength casing with a thick wall and a very good cementation. And then we'd like to know how other shales, other than those of the North Sea, behave in Saab tests. I'm trying to get my hands on material from North America, but I'd like to look at other parts of the world as well and see what they do. All of this has been well documented in SPE papers. To date, we've published about 5 papers or 6 papers, and we've got several of them planned. But please take a look at them. You can get them through One Petro. With that, I will end my presentation. I will thank particularly Metarock and Akshay Tombare, who's the genius doing these experiments, and Munir Alden, the head of the lab, for their support. We couldn't have done this all without them. Then the main rapid sponsors that have championed this work, have been Total Energies, Equinor, and Aker BP. Particularly Alex Lucas, I need to give him credit for the time when he was at Total Energies, has been a big supporter of this. And of course, this work is supported by all of the sponsors of the Rapid Industry Affiliated Program at UT Austin. And with that, I'll end my presentation. I'll thank my collaborators and my students for supporting me at UT. I thank you for your attendance and attention, and I'd be happy to take questions.
Many thanks indeed, Eric. Fascinating as ever. This is the subject that just keeps on giving. And the more we look into shales, the more potential applications we seem to find in terms of well integrity and how we can remediate wells, how we can use shales for well design, etc. So very many thanks to you for a fantastic presentation, and credit to you and all of your colleagues at the University of Texas and also at Metarock for this superb work that you've done over the past few years. We've got a few questions in the chat, I'm glad to say. One of them here from David Mackay, based in Aberdeen. And his question was about the time frames for the shale barrier to form, which you did touch on in your presentation. And I think when you mentioned using heat, we were looking at significantly accelerating the shale barrier. But if you were to upscale that to the wellbore scale, I think in the experiments we were talking about a day or less. What do you foresee in terms of what that would, how quickly that would form in the field? Would that be less than a week? Would you estimate?
Yeah, I mean, his question is specific to HPHT wells, right?
I think that was the next one I'm coming on to. I think the first one was the time frame at which the shale achieves a similar permeability and strength to cement, or comparable to cement. And would that always pass as a perf test?
Yeah, I mean the creep rate is as I said, is a function of in situ conditions, right? Temperature, pressure, in situ stress, and then of course the rock mechanical parameters, right? So it's different for different types of shales, right? You have to look at it each individually. So I can't give you any general guidelines on which type of shale under which type of condition closes the annulus at what time, right? You have to look at that individually. So for some shales, it will be very fast. I mean, this Shetland shale amazed us, right? How much faster it was than the Lark shale. But even the Lark shale closed in the annulus, right? But it took several months in order to do that.
I'm just thinking, okay, so I really love the fact that you consider all the geological factors. So when you mentioned that each shale is different, could you elaborate a little bit more about the mineralogy that determines the behavior?
Yeah, no, and if you go back to my presentation, right, there's this one slide where I show you the characteristics of shales that have been shown to kind of creep naturally, right, under in situ conditions. So those are typically kind of young shales, kind of Eocene age or younger, that still have retained significant amounts of smectite.
Right.
And have low strength, right, low compressional wave velocities, and so on. So there's a clear geological factor on this, right? There is a clear AAPG aspect to this, and still largely unexplored, I would say, because we've tested only so few materials, right?
Well, exactly, and I think that there's a lot of crossover between what we understand in terms of hydraulic fracturing and the behaviors of the different shale that we produce to what's happening under pressure and especially with geomechanical conditions. It's so fascinating. So much, you've done so much.
Yeah.
Thanks. The next question from David Mackay again relates to HPHT wells, and he's asking, would you get accelerated creep in HPHT wells based on temperature, or would you not, because it's used to that geothermal environment? And I guess would that temperature also create diagenetic effects, as you mentioned, the smectite-illite transformations that would prevent potentially that accelerated creep behavior from taking place?
Yeah, of course, that's the problem in an HPHT well, right? You have the temperature, but you have significant diagenesis there as well. So you will hardly see, certainly not for the deeper formations, any formations with significant free smectite. So I think in HPHT environments, it's going to be significantly limited. Maybe for shallow formations where you don't have HPHT conditions, will you see it? And there the effect of the well heating up, of course, during production will help. But for the deeper formations, the in situ conditions kind of preclude that shale creep will be occurring.
Right, yes. And a question from one of our SP technical section committee members here, Pierre-Edouard. Is there an absolute need for coring, or can suitable shale be identified from logs and basin studies?
Well, this is where we would like to get to, right? That you don't have to core, and you can do kind of simple tests, simple mineralogical tests, simple analysis to identify which shale is going to creep or not. But as I said, we haven't characterized the envelope of conditions and material properties sufficiently yet to do that. So for now, I really need more core to test. And then from that, in the future, I think we will be able to advise people based on just an XRD, maybe, right? And some understanding of the in situ conditions, whether a shale barrier will form or not. But I don't think we're there yet.
So at one stage, we might be able to look at cuttings material based on the XRD analysis of cuttings material and make an assessment based on the lab that you've done on multiple shale core samples. Right.
Yeah. But for that, as I said, I would like to test more shale core and get a better understanding. For instance, and I haven't told you about this, but we have done a test on a shale that had some smectite and some mixed layer smectite, but was very well cemented, extremely well cemented, and there was nothing that we can do to get it to creep. We threw everything but the kitchen sink at it, right? Combined thermal, chemical modification, pressure effects. We tried everything to make it to creep, and it didn't work. So there are clear situations where it will not work.
Great. Eric, in one of your earlier papers, you talked about, I think, what's now been coined the Van Oort method, or the Van Oort tests, where you can look at things like velocity anisotropy from your sonic logs, etc., and various other measurements to detect or at least predict whether a shale may form a barrier. Can you say a few more words about that approach? And I see with your new NSAB experimental apparatus, you're now starting to get very precise measurements of the ultrasonic behavior of the shale, and possibly even understand when the shale starts to form a barrier based on the bond index. Could you say a few more words about that?
Well, first of all, I can tell you that modesty would prevent me from calling it the Van Oort method. I've never seen it referred to like that, Alex. So, by the way,
that's maybe what I call it, Eric.
I'm just kidding. I'm not a modest person, right? No Dutchman is. And you wouldn't be a professor if you were a modest person. But But so, and I saw some questions here, there in the chat as well. So what is very interesting to operators, right, is qualification of the barrier without having to do explicit pressure tests, right? And that's been a big thing in the North Sea, and has been actively worked, for instance, with Haftil, the Norwegian regulator, with criteria being taken over, for instance, in standards like the NORSOK T010 standard. So the idea is that you only use kind of cased hole logs to identify the shale and to identify its barrier potential or its barrier capacity, right, without having to do casing perforation and explicit pressure testing. And that appears to be possible, right? So quite some nice work has been published by Aker BP in particular. And then, as I said, I've done some work on this myself, where through bond logs and ultrasonic logs, you can identify the shale and the shale properties around the casing. In fact, with the ultrasonic testing that we've done, we can actually pick up on the velocity anisotropy of the shale itself. So in the North Sea, you see that there is significant velocity anisotropy because of strength anisotropy in the formation. This will be, again, interesting to the geologists listening. So we can actually, in the ultrasonic log, pick up on the formation anisotropy behind the casing, the strength anisotropy through the dispersion of the ultrasonic signal, and then clearly identify that we have good bonding circumferentially around the casing, and clearly seeing the formation properties. And so that can help to qualify the barrier, right? And as I said, that is of course of key interest to operators, for not having to explicitly verify the barrier through pressure testing.
Building on that, taking a little bit more granular. So speaking of like the processes that are happening, have you taken a look at the surface tension in the shales, in the shale, that and the impact of the changes of pH or salinity over time, so that like bonds would start relaxing and have like a surfactant effect?
Susan, the sound quality of your microphone is really bad. So I
Oh, okay. Is this better?
Yeah, this is better.
Okay, I'm getting closer to it. I turned down my sound. Okay, so what I'm interested in is looking at, if you've looked at the pH or basically surface tension, and to look at over time if that changes as the salinity or the pH changes, and the surface tension causing eventual kind of a surfactant effect.
Yeah, I'm very happy that you're asking me this question, because I have, of course, had to make a selection of the work that I could present to you today. So one study that we've done is in looking into the effects of chemical fluid changeout in the annulus, right? And we see pronounced dependence of the creep behavior on changes in pH and ionic content in the annulus. And we think this has to do with ion exchange and modification of particularly the swelling pressure or swelling stress within the shale sample. So if you have a high pH fluid and or adverse ion exchange, where we're exchanging the shale for less inhibitive ions, or an excess of inhibitive hydrated ions, we've seen significantly accelerated creep. And it's in one of my papers, actually co-written with Alex, where that is clearly discussed. So
oh, goodness. I'm checking it out now.
Yeah.
So Eric, yeah, I think those fluids that you identified were the silicate-based fluids and the supersaturated KCl.
Yeah. So we saw significantly accelerated creep with lithium silicate, which is high pH, and lithium is very much hydrated, has very high charge density, so it structures water around it in a very big way, creating hydration stress within the shale. And then we saw amazing results also with a fully saturated KCl solution. KCl is normally thought about as being very inhibitive, which it is, but if you cram an excess of salt into the shale matrix, all being hydrated ions, then you actually also induce the increased hydration stress. And all of that kind of reduces effective stress in the shale and drives it towards the failure state that allows it to creep faster.
That's great. I appreciate this is the P&A technical section today, but just touching on wellbore construction, if we were to use such fluids in the cement pre-flush, is that something you would advocate for in wellbore construction?
So
actually utilizing part of the primary isolation strategy.
Yeah. So thinking about utilizing shale barriers in the future, right? What you think about is actually deliberately cutting top of cement short and having a spacer above the cement or ahead of the cement that covers the shale section, and then accelerates the barrier formation. Something like a lithium silicate or a saturated potassium chloride solution, provided, of course, we verified that those are indeed the materials that will accelerate the creep. So that's actually being seriously discussed with some of the rapid sponsors right now, right, on doing that. That would, for instance, be a way to do this, for instance, for carbon storage wells.
Absolutely, that could be fascinating and a fantastic application.
Yeah, and it's completely contrary to kind of conventional barrier thought, right? About how you conventionally think about barriers, right? I mean, cutting the cement barrier short, right? Just to accommodate a shale barrier. I mean, that feels very alien to us, right? But that might actually be the best thing for long-term well integrity. So we need a little bit of a paradigm shift in that regard, right?
And also, we need to send you more core material so you can make better assessments of the likelihood of incorporating that approach in our well designs.
Yeah.
Excellent. Right. One last question. You've been very kind, Eric. We are overrunning, but there has been a really fruitful discussion. One last question here. Could we use sidewall cores as an alternative to regular overburden cores for your work?
If you have high quality, well preserved sidewall cores, you could potentially use those. Yeah, that's possible. Again, preservation is important, right? If somebody is going to get sidewall cores, I'd like to talk to them about preservation techniques, right? Because we really need high quality core material. The materials that I've presented to you, the Lark Shale and the Shetland Shale, had exceptional core preservation, right? And that is necessary. You can't just allow a core to be dried out and falling apart and breaking up, right? That's not good. So you need to core very carefully and then store in an inert material, preferably kind of a base oil, for it not to deteriorate and dry out.
Okay, so operators out there, please heed Eric's request there. If you have any suitable material that you'd like to share and present to his program at the University of Texas, that would be something you'd be doing for the greater good of all of us as SPE members and practitioners in well P&A. So I think probably we've reached the point, Eric, where we need to wrap things up. You've been very kind to us, staying on the line a little bit longer into your day, so thank you very much. So we'd like to thank you on behalf of myself and my co-host, Susan, and also colleagues in the P&A technical section. We'd like to thank you all for joining today, particularly yourself, of course, Eric, for a wonderful presentation, and everyone online, of course, for the live questions and comments. A really good discussion there. So thanks very much to all of you. We hope to see you all again at one of our next webinars. So please stay tuned. Any further comments before we go? Pierre-Edouard and Wakas, I see you've joined the floor here.
No, I will
No?
just say that this is a developing field, which is absolutely fascinating. We will have more webinars on the use of shales, marine clays, and bentonite in the future. So stay tuned for some of the dates, and we hope to show you interesting content.
No, thanks a lot for joining all the audience. Thanks, Eric, for presenting. We will have this session recorded both on the LinkedIn and as well as on YouTube, and we'll share it today.
And just thank you. What a great team.
Great, wonderful, thanks. I think Pierre-Edouard will conclude our event with a short video from the SPE.
Yep.
And
see you next.
On behalf of everyone online, bid you all farewell. Next time. Thanks.
You know, people ask me why they should join SPE, and what I tell them is that SPE is absolutely essential. Frankly, if SPE didn't exist, somebody would have to go out and create it. When you graduate with a technical degree, a petroleum engineering degree, or other engineering degree, you get a lot of really good knowledge that gets you started on your career, and you learn a lot on the job. But the jobs that we have in this industry, they're really quite difficult. And you've got to have other resources, either to solve specific problems you might be having at the moment, or to better understand how to solve, daily issues that you work on. SPE provides opportunities to learn about new things that people are working on. There are great articles in JPT Magazine and the other magazines that we have that are really useful. If you're not reading JPT every month, I tell you it's essential to do that to keep up with the technology. We have excellent conferences where you can learn from people who have solved very difficult problems in our industry. And doing that is just incredibly important and incredibly useful. To me, I don't see how you can be an engineer working in the petroleum industry and not find value in the resources and the opportunities that SPE provides. It's an opportunity to meet people who can help you in the industry, and it's an opportunity to get the knowledge you need to be successful.